Yes, it is possible to have a parallel path with bonding wires. Parallel bonding paths can increase the risk of electrical shock if one bonding wire fails. They can also create ground loops, which can cause interference in sensitive electronic equipment. It is generally not recommended to create parallel bonding paths. Bonding is required when there is a change in material. Copper is required to be bonded at the following points. Firstly, the first point of entry into the building. Secondly, where it transitions to another type of pipe. And thirdly, is directed by the local electrical code. Bonding every fixture is not required. If the manifold is large enough to be considered an extension of the water service, typically 1.25 inches or larger, it should be bonded. Smaller manifolds may not need to be bonded if they are physically close to a bonded fixture or pipe. Bonding every faucet, sink, and toilet is excessive and unnecessary. The risk of a 12-inch piece of pipe becoming energized under a toilet is extremely low. Bonding is important for safety, but it should be done correctly. Parallel bonding paths should be avoided. Follow the local electrical code and common sense when bonding plumbing systems. Overly excessive bonding requirements are not practical or necessary. The purpose of bonding and grounding is to create a low impedance path for fault current to return to the source, allowing the overcurrent protective device, such as a circuit breaker or fuse, to trip and clear the fault. This helps to prevent electrical shock hazards and minimize the risk of fire. Bonding refers to connecting non-current carrying metal parts together to create an electrically conductive path. This ensures that all metal parts are at the same electrical potential, minimizing the risk of voltage differences that could cause a shock. Grounding refers to connecting the electrical system to the earth, providing a reference point for voltage and helping to stabilize the system. The National Electrical Code, or NEC, provides specific requirements for bonding and grounding to ensure electrical safety. Article 250 of the NEC covers grounding and bonding. The NEC is updated every 3 years, so it's important to refer to the latest edition. The 2014 NEC, which is relevant here, provides guidelines for proper bonding and grounding techniques. When dealing with metal water piping systems, the NEC requires bonding to ensure electrical continuity. This is because metal water pipes can become energized due to faults in the electrical system, and bonding provides a path for fault current to flow back to the source. Section 250.104 of the NEC covers bonding of metal water piping systems. It requires that metal water piping systems that are likely to become energized be bonded to the grounding electrode system. The grounding electrode system typically consists of a ground rod, ground ring, or metal underground water pipe. The bonding conductor must be sized according to NEC Table 250.102. C1, based on the size of the service entrance conductors. The bonding connection should be made at the point where the water service enters the building or at a point within 5 feet of the entrance. This ensures that the entire water piping system is effectively bonded. When plastic water piping is used, bonding requirements change. Since plastic is non-conductive, it cannot carry fault current. However, any exposed metal parts of the water system, such as copper pipes or manifolds, still need to be bonded. If there is a transition from plastic pipe to copper pipe, the copper pipe must be bonded to the grounding electrode system. This is because the copper pipe can still become energized due to faults in the electrical system. The bonding connection should be made as close as possible to the transition point. When dealing with multiple units or dwelling units, it is important to ensure that each unit has its own grounding electrode system. This helps to prevent ground loops and ensure that each unit is properly protected. Each unit should have its own grounding electrode conductor connected to a ground rod or other approved grounding electrode. The grounding electrode conductor should be sized according to NEC Table 250.66, based on the size of the service entrance conductors. When bonding metal water piping systems in multiple units, it is important to avoid creating parallel paths. Parallel paths can occur when multiple bonding conductors are connected to the same water pipe. This can create a situation where fault current can flow through multiple paths, which can increase the risk of electrical shock. To avoid parallel paths, it is recommended to bond the water pipe at a single point. This can be done by connecting a bonding conductor from the water pipe to the grounding electrode system at the point where the water service enters the building. When dealing with small sections of copper pipe, such as those used under sinks or for outside spigots, it is generally not necessary to bond each individual section. However, if the sections of copper pipe are connected to a larger metal water piping system, the entire system should be bonded. The NEC does not provide specific guidelines for the size of the copper pipe that needs to be bonded. However, as a general rule, if the copper pipe is large enough to be considered an extension of the water service, it should be bonded. This typically applies to pipes that are 1.25 inches or larger in diameter. When dealing with manifolds, the same principles apply. If the manifold is large enough to be considered an extension of the water service, it should be bonded. This typically applies to manifolds that are 1.25 inches or larger in diameter. Smaller manifolds may not need to be bonded if they are physically close to a bonded fixture or pipe. It is important to use appropriate bonding methods and materials. Bonding conductors should be made of copper or other approved materials. They should be sized according to the NEC and securely connected to the metal parts using approved bonding connectors. Bonding connectors should be listed for the purpose and installed according to the manufacturer's instructions. When making bonding connections, it is important to clean the metal surfaces to ensure a good electrical connection. This can be done by using a wire brush or other abrasive material to remove any dirt, grease, or corrosion. The bonding connector should be tightened securely to ensure a good electrical connection. It is also important to protect bonding connections from corrosion. This can be done by applying a corrosion inhibitor to the connection after it has been made. The corrosion inhibitor will help to prevent the formation of rust and other corrosion products, which can weaken the electrical connection. When dealing with sensitive electronic equipment, it is important to minimize the risk of ground loops. Ground loops can occur when there are multiple paths for ground current to flow. This can create noise and interference in the electronic equipment. To minimize the risk of ground loops, it is recommended to use a single-point grounding system. In a single-point grounding system, all of the electronic equipment is connected to a single grounding point. This helps to prevent ground current from flowing through multiple paths. It is also important to use shielded cables and connectors to minimize the risk of noise and interference. Shielded cables and connectors have a metal shield that surrounds the conductors. The shield is connected to ground and helps to block electromagnetic interference. When installing bonding and grounding systems, it is important to follow all applicable codes and regulations. The NEC provides specific requirements for bonding and grounding, and it is important to comply with these requirements to ensure electrical safety. It is also important to consult with a qualified electrician or electrical engineer to ensure that the bonding and grounding system is properly designed and installed. A qualified electrician or electrical engineer will have the knowledge and experience to design a bonding and grounding system that meets the specific needs of the application. In addition to the NEC, there may be other local codes and regulations that apply to bonding and grounding. It is important to check with the local authorities to ensure that the bonding and grounding system complies with all applicable codes and regulations. Proper bonding and grounding are essential for electrical safety. By following the guidelines in the NEC and consulting with a qualified electrician or electrical engineer, it is possible to design and install a bonding and grounding system that will protect people and property from electrical hazards. The bonding wire, also known as a grounding conductor, is a critical component of electrical safety. Its primary function is to create a low-impedance path for fault current to return to the source, enabling overcurrent protection devices to quickly trip and disconnect the circuit in the event of a fault. This prevents dangerous voltage buildup on metallic surfaces, reducing the risk of electric shock. The size of the bonding wire is determined by the size of the service entrance conductors, as specified in NEC Table 250.102. C1. Using an undersized bonding wire can significantly compromise its effectiveness, potentially leading to higher impedance and slower fault current clearing times. The material of the bonding wire is typically copper. due to its excellent conductivity and resistance to corrosion. Aluminum is also permitted, but it must be appropriately sized and terminated to ensure a reliable connection. The bonding wire must be securely connected to the grounding electrode system, which includes elements like ground rods, ground rings, or the metal underground water pipe. The connection point should be readily accessible for inspection and maintenance. The NEC mandates specific requirements for the protection of bonding wires. They must be protected from physical damage, such as being run through conduit or otherwise shielded from impact. In corrosive environments, the bonding wire and its connections should be protected with appropriate corrosion inhibitors to maintain their integrity. The concept of impedance is crucial in understanding the effectiveness of a bonding system. Impedance is the total opposition to current flow in an alternating current circuit, encompassing resistance, inductive reactance, and capacitive reactance. A low impedance path ensures that fault current can flow easily back to the source, facilitating rapid tripping of overcurrent protection devices. High impedance, on the other hand, can impede fault current flow, delaying the tripping of protective devices and increasing the risk of electric shock. Ground loops are undesirable current paths that can occur when multiple grounding connections are made to the same piece of equipment or system. These loops can create circulating currents that introduce noise and interference into sensitive electronic equipment. To avoid ground loops, it's essential to establish a single-point grounding system where all grounding connections converge at a single location. This minimizes the potential for circulating currents and ensures a clean, stable ground reference. In addition to water pipes, other metallic components in a building, such as gas pipes and metal conduits, also require bonding. Gas pipes are bonded to prevent them from becoming energized due to electrical faults. Metal conduits, which house electrical wiring, are bonded to provide a path for fault current to flow back to the source. The NEC provides detailed guidelines on the bonding of these metallic components. The grounding electrode system serves as the foundation for the entire bonding and grounding network. It provides a connection to the earth, which serves as a reference point for voltage and helps to stabilize the electrical system. Common grounding electrodes include ground rods, which are driven into the earth, ground rings, which are buried in a loop around the building, and metal underground water pipes, which are connected to the water service. The selection of the appropriate grounding electrode depends on soil conditions, local codes, and the size of the electrical system. Regular inspection and maintenance of the bonding and grounding system are crucial to ensure its continued effectiveness. Connections should be checked for tightness and corrosion, and any damaged or deteriorated component should be replaced promptly. Periodic testing of the grounding electrode resistance can also help to identify potential problems. The NEC provides specific requirements for the testing and maintenance of grounding systems. In summary, a well-designed and properly installed bonding and grounding system is essential for electrical safety. It provides a low impedance path for fault current to return to the source, minimizes the risk of electric shock, and protects sensitive electronic equipment from noise and interference. Following the guidelines in the NEC and consulting with a qualified electrician are crucial for ensuring the effectiveness and reliability of the bonding and grounding system.